All right, strap yourselves in, because today we're diving deep, really deep into the Big Bang.
Oh yeah, we're going way beyond the basics here.
Exactly. We're assuming you've got what is the Big Bang 101 down pat. So we're going to unpack this awesome presentation called The Big Bang Explained. It's packed with insights, and we'll pull out the most mind-blowing bits.
It really is a fantastic resource. Helps us put together the story of, well, everything.
Okay, so first things first. If the Big Bang wasn't some massive explosion, why do we call it a bang anyway?
You know, the name's a bit misleading. The Big Bang wasn't an explosion in space. Think of it more like the expansion of space itself. Imagine this. A tiny, unbelievably dense point, holding all the matter and energy in the universe, suddenly expanding outward in every direction.
So instead of stuff scattering through space, space itself is stretching, carrying everything with it.
Exactly. And that expansion, still happening today, billions of years later. Which brings us to cosmology, the ultimate detective work, trying to trace the universe's evolution from that initial expansion to the intricate structures we see today.
So the Big Bang is basically the heart of cosmology, the origin story.
You got it. And one of the biggest breakthroughs in cosmology came from Edwin Hubble, working with the Hooker telescope, the most powerful telescope of its time.
He was peering deep into space, right?
Deep. And what he saw changed everything. First, he confirmed the existence of galaxies beyond our own Milky Way, proof that our galaxy is just one of billions in a vast and, get this, expanding universe.
Talk about a mind-blowing realization. Entire galaxies out there filled with stars and planets. We may never even see them.
And that's just the first of his discoveries. His second was even more groundbreaking. Hubble observed something called redshift, which basically means light from distant galaxies is stretched towards longer, redder wavelengths.
Wait, so it's like the Doppler effect, but with light instead of sound.
You got it. As a galaxy moves away from us, its light waves stretch out, shifting towards the red end of the spectrum. The farther away a galaxy is, the faster it's moving and the greater the redshift. That's Hubble's law.
So by measuring redshift, we can actually figure out how fast galaxies are moving away from us, like a speedometer for the universe.
Exactly. And this redshift, major evidence for the Big Bang. It's not just an explosion in space, it's space itself stretching, carrying everything along.
Okay, that makes the whole bang idea make more sense. But redshift isn't the only evidence for the Big Bang, right? There's something about an afterglow, some kind of cosmic radiation.
You're talking about the cosmic microwave background radiation, or CMB. It's like a faint echo of the Big Bang, this whisper of radiation that's all over the universe.
It's hard to imagine something so faint could be so important. How is it even discovered?
It was a happy accident, actually. In 1965, two scientists, Arno Penzias and Robert Wilson, were working with this massive antenna. They kept picking up this weird noise, a constant hiss.
A hiss. I bet they thought their equipment was messed up.
At first they did. They tried everything to get rid of it, even cleaned pigeon droppings out of the antenna. But the hiss stuck around. Finally, they realized what they were hearing was the afterglow of the Big Bang itself.
Wow, what they thought was just interference turned out to be a groundbreaking discovery. Science is full of surprises.
It really is. And this discovery kicked off a new era in cosmology. Scientists wanted to study the CMB in more detail, which led to a bunch of incredible space telescopes.
Each one more powerful than the last, I'm guessing. This is where COBE, WMAP, and Planck come in.
You got it. Each mission was like zooming in on a map of the early universe, revealing the CMB in greater and greater detail. These telescopes allowed us to measure tiny fluctuations in the CMB's temperature, which hold clues about the seeds of structure in the early universe.
So by studying these tiny temperature variations, scientists could begin to understand how galaxies and clusters of galaxies form.
Exactly. It's like looking back in time to see the birth of the structures that make up the universe today. But these telescopes also confirm something pretty unexpected.
Wait, what could be more unexpected than hearing the echo of the Big Bang?
Well, they confirmed that the universe isn't just expanding, its expansion is accelerating. Something's pushing everything apart, working against gravity, and that's where things get really interesting and kind of spooky.
Okay, you've definitely got me hooked. We're talking about dark matter and dark energy.
You got it. Get ready, because things are about to get really mind-bending.
Let's do it. I'm ready to explore the deepest secrets of the cosmos.
All right, welcome back. Now we've explored the evidence for the Big Bang and the expanding universe. It's time to tackle those big mysteries. Dark matter and dark energy.
I'm ready for it. Last time we left off with this wild idea. Everything we can see, stars, planets, galaxies, the stuff we're made of, It's just a tiny fraction of the universe.
It really is a humbling realization, isn't it? Makes you wonder what else is out there.
Definitely. So let's start with dark matter. What do we actually know about it? How do we even know it exists if we can't see it?
Well, we know it exists because of its gravity, its effects on the visible stuff. Astronomers have observed galaxies rotating way faster than they should based on the amount of visible matter.
So there's got to be something else there, some invisible matter, providing that extra gravity to hold them together.
Exactly, like an invisible scaffolding holding the universe together. And we see the same thing in clusters of galaxies. The way they move and interact tells us there's a lot more mass there than we can see with our telescopes.
Okay, so it's there, but trying to understand something you can't even see sounds incredibly difficult.
It's one of the biggest mysteries in astrophysics. Scientists have been trying to detect dark matter particles directly for decades, but it's like searching for a whisper in a hurricane.
So far, no luck.
Not yet. There are a bunch of theories about what it could be. One popular candidate is WIMPs, which stands for Weakly Interacting Massive Particles.
WIMPs. Sounds kind of cute for something so mysterious.
Ha, yeah, don't let the name fool ya. WIMPs would interact very weakly with ordinary matter, making them super hard to detect. It's like they're passing right through us without a trace.
Okay, so dark matter's a real head-scratcher. But the universe decided to throw in another curveball, right? Dark energy.
Oh yeah, don't forget about dark energy. This mysterious force is causing the universe's expansion to accelerate, working against gravity.
It's like space itself is being stretched by some invisible hand.
And the weirdest part is that the expansion is getting faster over time, meaning dark energy's influence is growing.
Okay, that's a little unsettling. What happens to the universe then? Does it just keep expanding forever?
That's the big question, and the answer depends on the nature of dark energy. If its density stays the same, then yeah, the universe will probably keep expanding indefinitely.
So galaxies will just keep getting farther apart, becoming like isolated islands in this massive, empty space.
That's one possibility, often called the Big Freeze scenario, but it's not the only one.
Uh-oh. What other options are there?
Well, there's the Big Rip, where dark energy gets so strong that it overpowers everything else, tearing apart galaxies, stars, even atoms.
Okay, that's kind of terrifying. Any other slightly less catastrophic possibilities?
There's also the chance that dark energy's density might decrease over time, eventually letting gravity take over and stop the expansion. This could lead to a big crunch, where the universe collapses back on itself.
So the Big Bang in reverse.
Exactly, ending where it all began.
Okay, so we've got the Big Freeze, the Big Rip, and the Big Crunch. Sounds like dark energy holds the key to the universe's fate, and we're still trying to figure it out.
It's a challenge, but that's what makes cosmology so exciting. Every new discovery leads to more questions.
It's not just theoretical, though, right? Scientists are actually searching for answers about dark matter and dark energy with experiments and observations.
Absolutely, and in part 3, we'll dive into some of that latest research. We'll discuss what the future holds for understanding these cosmic enigmas.
All right, we're back, ready to explore the research that's pushing the boundaries of our understanding of the universe.
We're diving into the world of particle physics, massive telescopes, some of the brightest minds out there.
It's like the final level of a cosmic video game.
Ha! I like that analogy.
So where do we even start? We're talking about invisible stuff, forces that seem to break the rules of physics as we know them.
It's a huge challenge, but scientists are tackling it from all angles. One way is to keep hunting for those dark matter particles directly.
Right, those underground detectors searching for WIMPs.
Oh.
Any luck so far?
The search is ongoing, the technology is always improving. These detectors are getting more and more sensitive, trying to catch the faintest whisper of a dark matter particle.
So imagine one of these detectors actually picks up a WIMP signal. What would that mean?
It would be a complete game changer. It would prove that dark matter is made of particles, opening up a whole new area of particle physics.
Wow, a major breakthrough. But what if these detectors don't find anything? Are there other ways to study dark matter?
Definitely. Scientists are also studying the large-scale structure of the universe, looking for the gravitational fingerprints of dark matter. They're mapping out where galaxies and clusters of galaxies are, creating a 3D map of the cosmic web.
So by seeing how these structures are arranged, how they move, we can figure out where the dark matter is.
Exactly. It's like shining a flashlight on a spider web in the dark. You can't see the web itself, but you can see how the light reflects off the threads.
I love that analogy. And what about dark energy? Are scientists working on that too?
Oh, absolutely. Those distant supernovae we talked about, they're crucial for studying dark energy.
Right, those exploding stars that act like cosmic yardsticks.
Exactly. By observing them at different distances, we can track how fast the universe has been expanding over time. That helps us figure out if dark energy's influence is constant or changing.
So we're using exploding stars to map out the history of the universe's expansion and see how dark energy fits in.
It's pretty amazing, right? And it's not just supernovae, scientists are using other techniques too, studying the cosmic microwave background radiation, how galaxies cluster together, all to understand dark energy.
It sounds like we're living in a really exciting time for cosmology.
It is. Every new observation, every new piece of data gets us closer to understanding dark matter and dark energy.
Well, this deep dive has been an incredible journey. We've explored the beginning of the universe, those mind-blowing mysteries of dark matter and dark energy. It's been amazing to learn about all the research that's going on.
It's a journey that never really ends, the quest to understand the universe. Every answer just leads to more questions, and that's what makes it so captivating.
Exactly. So to our amazing listener, we hope this deep dive has sparked your curiosity. Keep looking up, keep asking questions, and never stop exploring the wonders of the cosmos.